Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege. This is a bad timing having the Dodgers logo pop up. Giants, baby. Let's go. It's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we do the section 5.1 to 5.4 quiz review in IM1. This is solving systems of linear equations. We've solved by graphing, substitution method, and elimination method. Section 5.4 involved the special cases. And because these show the sections by number, I'm sure it's going to show when section 5.4 comes up. So I guess you'll know when special cases come up, which is kind of too bad. That means you also know when things will have one solution and we'll list them. But you know what? We practice some things, we get them ready for a quiz or whatever you want to do before we move forward into the latter half of the chapter. Jump to the description section down below if you'd like to see these 15 problems at their work, especially because, sometimes on my PDFs you can't see them really as well. So download that PDF, print it out, check it out, what have you. Also print out graph paper if we need it. I don't know if we do, but 15 questions total. Let's go ahead and get started. We are going to start with numbers 1, 2, and 3. It says use the graph to solve the system of linear equations, so we don't graph ourselves. It does say check your solution, and I think at the time we did it physically, so I'll do it here as well. What I mean by physically is actually plug the numbers in. The idea behind this is there is only one xy that'll work for this system of linear equations. Y equals negative 1/3 x plus 2 is this line that's going down right here. Y-intercept of 2, slope of down 1 over 3, boom, like that. And then y equals x minus 2 has a y-intercept of negative 2 and a slope of 1, up 1 over 1 like that. And eventually they intersect at that place right there. This guy right here is the point of intersection. I forget if I copied and pasted these at the time. I'll just leave it there. That point of intersection is 3, 1. When x is 3, y is 1, that should work for both equations simultaneously. My double check for that is I'm going to go and, that's the answer. My double check for that is I'm going to go ahead and substitute in the first equation. 1 for y, 3 for x, and see if the left side equals the right side. Negative 1/3 times 3 is negative 1. Negative 1 plus 2 is 1, and 1 equals 1 checks out. In the bottom equation, we have 1 for y, and 3 for x. 1 equals 3 minus 2. 1 equals 1. That one checks out. So that's my double check of those solutions. These are the only times I'm going to do the double check physically instead of mentally, I imagine. Number 2, y equals 1/2 x minus 1. Y equals 4x plus 6. Also both in slope-intercept form. In fact, all these are in slope-intercept form here. 1/2 x minus 1 is this guy right here. Negative 1 and up 1 right 2, but also down 1 left 2 right here. Looks to be intersecting with this other line. They already drew the graph. Y equals 4x plus 6. You can't see the plus 6 up there, but let's go down 4 left 1. We hit negative 1, 2. Down 4 left 1. We hit this guy right here. So although the window range doesn't give us everything that we want, it does give us the point of intersection, which is negative 2 for x, negative 2 for y. That is said point of intersection. And look, I'm only showing the graphing portions because I don't know if I'm going to graph later. Yes, the point of intersection is all that matters for us for the set, but I want to make sure you know which equation goes to what and how we're checking it. So a double check on this one, negative 2 equals 1/2 times negative 2 minus 1. There's no reason for this to be wrong. Half of negative 2 is negative 1. Negative 1 minus 1 is negative 2, and that's all good. For the other equation, we have negative 2 equals 4 times negative 2 plus 6. Or negative 2 is negative 8 plus 6. Negative 2 equals negative 2 there as well. Okay. Number 3, the top equation says y equals 1. Now, as a reminder, that means y equals 0x plus 1. Slope of 0 means horizontal line. No rise. And that's what a y equals equation has. It has no rise, all run. Y-intercept is 1, and it goes left to right forever like this. And this one happens to share the same y-intercept, has some slope up 2 over 1. Doesn't matter much because they intersect at the value of 1 for y. And that's the only y value that would have been possible when there's an equation that says y equals 1 on it. There's no other possible y it could have been. The x just so happens to be 0 at the same time, though. 0, 1 is the answer to that one. Let's double check by plugging in 0 for x and 1 for y in the first equation. Mr. Robinson, I have nowhere I can plug in 0 for x. Well, then don't do it. Plug in 1 for y, you get 1 equals 1. And then 1 equals 2 times 0 plus 1. You can plug in 0 for x right there. 2 times 0 is 0. 1 plus 1, or 0 plus 1 is 1. 1 equals 1 there. That also checks out. So we didn't graph ourselves, although I did without doing it. Maybe I don't need the graph paper, actually, on these. We'll see if we actually do. Let's move to numbers 4 through 6, where we solve by substitution. This was section 5.2, and yes, they are forcing substitution on us. As much as you might have learned out of elimination method, we are not going to solve using elimination on here. So, in solving using substitution, let's do what we know how to do with it. The substitution method entails taking a variable, getting it isolated, in this case the y is isolated, and substituting the expression in for y in the other equation. It's not always y, but whichever variable is isolated or that you like to isolate. So let's rewrite that second equation, negative 2x plus, and instead of y, we'll put x minus 4, there's the substitution, and that equals 18. So it's a rewrite of the equation without y. Our goal has been achieved. We've now gotten one equation with one variable for which we can now solve. Negative 2x plus x is negative 1x. And I've stated this on all the sections leading up to this, guys. I'm no longer showing the actions in between. Although I'm going to add 4 to both sides, I'm not going to write plus 4 and plus 4. So adding 4 to both sides gets me this, and dividing both sides by negative 1 gets me this. So x is negative 22. But as we've seen in solving by graphing from section 5.1, guys, we should get an x and a y. Our final answer should be an ordered pair, ordered pair, ordered pair. So let's substitute negative 22 for x, preferably in this equation here. It's very easy to solve for y off that. And we get negative 26. We got an x, we got a y. There's our final answer, ordered pair. If we graph these, this is where they'd intersect. Pretty far off the conventional place that we'd see them, so maybe that's why we use this method instead. Number 5, we'll also solve using substitution. However, on number 5, there is no isolated variable. So we take our pick out of the litter as far as which variable you would like to get by itself. We have multiple options here. I could solve for this y here, but eventually I'd have to divide things by 2, which means dividing a 1x by 2 leaves me a fraction. I don't want to get that y by itself. Getting this x by itself takes one step, subtracting 2x over. Not too bad, but it would lead everything with negative, and you'd have to subtract into there. Not my preferred one. I think getting this y by itself is probably my favorite. It adds this x over. It adds this x over, making that one positive. And it took one step to do it. Now that means I do need to substitute x minus 5 in for y in the top equation. That does require distribution. Oh well. But that's probably my preferred, all told. Don't spend too long trying to think about which one to do, but really just try and avoid having any fractions. 2 times x, 2 times 5 happens here. 2x plus 1x happens here. We're now going to do 2 more steps, adding 10 to both sides. 10 minus 4 is 6. Dividing both sides by 3, you get x equals 2. As we've already seen, we now need to solve for y. And, you know, solving with substitution method is quite nice because you do get that other variable by itself. So straight up, 2 minus 5 gets us negative 3. We're there. So 2 comma negative 3 is our solution to that set. And there's more than one way to solve that, but that is the only solution to that one. Number 6, our last one on substitution before, I don't know, maybe they have a set on using any method or maybe on word problems. 3x minus 5y equals 13. I don't really quite see anything I'd like to get by itself there. But on the next one, x plus 4y equals 10. The only one that's really fast to get by itself is just this x right here. So let's go ahead and subtract 4y over. 10 minus 4y. So we're going to, as my favorite saying, take that expression and shove it up your x. The other x that we have right there. Substitute it, only have an equation with y's in it. 3 times this x minus 5y equals 13. Let's solve for y, use that to solve for x by plugging it back into there after. So by distribution, we will have 30 minus 12y. Combine the y's, 30 minus 17y. Let's go a faster route. I'm going to add 17y to both sides and subtract 13 from both sides. You get 17 there. Divide both sides by 17. We get y equals 1. Y equals 1. X is solved by subtracting, well, substituting y, but 10 minus 4 times 1. 10 minus 4 is 6. X equals 6. And ordered pair, never forget that. You've never seen me miss that case. Word problems, we don't write in ordered pair. And it looks like number 13, probably to 15, has word problems. We don't write an ordered pair for those ones. We use units and such. But non-contextual problems, ordered pairs, please. Those were substitution. That was section 5.2. Let's move forward. Numbers 7 through 9, we're going to solve using elimination. Now, the elimination method, a lot of people do love it. You probably saw number 5 and you said, I want to use elimination here. or even number 6, but we were forced on substitution. And I don't know, depends on your teacher. You might be forced by hand to use one versus the other. I generally don't force the hand, but you probably want to know both in general. Anyway, the elimination method's pretty cool. As long as you have variables lined up, constants lined up, equal signs lined up, you can add to both sides of these equations, and if variables eliminate along the way, go ahead and make that happen. I'm not going to get deep into why I did that during the section itself, but y minus y eliminates. These are gone. You now have one equation with one variable. X minus 3x is negative 2x. 4 minus 8 is negative 4. Need I remind you, we did add, but we added negatives. So what I say is you treat the signs as they are when you add. So adding a negative becomes subtraction. Negative 2x equals negative 4, therefore x equals 2 when you divide both sides by negative 2. Now, just like the substitution method or any system of equations, we do need the y, so we have to substitute x into an equation. I like the top equation. 2 plus y equals 4. Subtract 2 from both sides, you get y equals 2. So 2 for x, 2 for y, ordered pair, there you go. Okay. Number 8. Number 8 doesn't have quite the luxury that number 7 does in this one facet of if I added right now, would any variable eliminate? And the answer is no. If I added, whoa, I wanted to undo just the y. If I added right now down these lists, would it belong to the system? Sure. But would it eliminate anything? No. I'd get 5x, I get 6x plus 9y equals 15. And that don't apply, that it doesn't help. What I can do is eliminate a variable if I manipulate an equation, do something to both sides of it. Such as take the top equation, I could multiply everything by negative 5 to eliminate the x's. I'd get a negative 5x with positive 5x. Not bad. If you want to keep the numbers a little bit smaller, I could multiply everything by negative 2 and eliminate the y's. And I choose negative so that way I can treat the signs as they are. Negative 6y right there. And negative 2, don't forget to multiply the 1 by the negative 2. Now, just ignore that 1 for now. These y's can eliminate. 6y minus 6y is 0. 5x minus 2x is 3x. 14 minus 2 is 12. Divide by 3. You get x equals 4. In terms of solving for y, you can substitute in any of these three equations that you have. I like the top equation that I crossed out. 4 plus 3y equals 1 has the most small numbers. Subtract 4, divide by 3, you get y equals negative 1. As you can see, my efficiency is really paying off, and it has been the entire chapter when it comes to not showing the actions in between. No more. No more. I hope that you guys are learning off of that as well. All right, number 9, last one for elimination, at least by force. Same thing. If I add down these lists right now, nothing will eliminate. But this one gets a little bit trickier even, and I like the progression that they had. One where it's clear as day what you can do. After this, it's a little bit more as you go. See, last time I could have multiplied the top equation by negative 5, top equation by negative 2, anything like that. Boom, you eliminate. Here, 5 is not a common multiple of 2. It's not a multiple of 2. 3 is not a multiple of 2. So here, you got to probably change both equations if you want to get done what you want. Would you rather eliminate x's or y's? It's a your choice thing. I prefer y in this problem for 2 reasons. Number 1, smaller numbers out. 2 and 3 have a least common multiple of 6, whereas 2 and 5 have a least common multiple of 10. That means smaller numbers to get out. Number 2, the signs are already opposite of each other. So I don't ever have to multiply by a negative. You know that that can lead to some issues. If I multiply the top equation by 2 and the bottom equation by 3, I will get additive inverses on y, and that'll get me to what I want. 4x minus 6y equals negative 10. And on bottom, 15x plus 6y equals positive 48. Like that. The y's eliminate. You get 19x here, 38 here. Divide by 19, you do get x equals 2. So it still cleans up, and I still feel good about things. Can you have fraction answers? I guess. They've been very nice in not having fraction answers here. Every so often, it wouldn't hurt to have one, just to say that they exist. Anyway, for y, where do you plug it in? It's kind of your call. Let's use that bottom equation right there, 5 times 2. I'm looking at where I can have the most positives out. This is where, as much as you may love the elimination method, now I would never solve this using substitution method, but in getting a variable by itself, it's a few less steps in solving for the other variable. I'll show you up top before I move forward to the next set of problems. So 2 for x, 3 for y, boom, you have it. You can see once I substituted 2 for x, it took more work to get there, whereas on a substitution problem, like say it's number 6, X is already like by itself, so it's like a faster solving for me. That's what I always like about substitution on that. But I like elimination when elimination is good. In these problems, elimination was very good. Okay, numbers 10 through 12 is what? Solve the system of linear equations. So this time they let us use any method. The only thing, though, it says section 5.4. Now, 5.4 was special case situations. We expect a lot of no solution or infinitely many solutions to arise here. So that's the one caveat. Although I can choose my own method, I also don't expect to write ordered pairs as answers here. Now, if you want to use elimination method, that's cool. We can take the top equation, multiply by -1, change up the signs. Negative x plus y is -1 like that. Just ignore that one now and add down the lists. X minus x is 0. Negative y plus y is 0. 6 minus 1 is 5. Did I mess up? I did not. 0 equals 5. Left side had all the variables cancel. Right side is not the same as the left side. This is a no solution case. Now, if I graphed it, which I could have, and that's a method I could be choosing. I probably should look at that every so often. If I graphed these, I kind of want to just get the idea of the graph. If I graphed these, this would have an x-intercept of 1, y-intercept of -1, x-intercept of 6, y-intercept of -6. So these would have been like a line right here and a line right here, and they just would have been parallel and never intersected. And that's graphically what these things look like as a whole. Okay, that's what's going on with that. I'm trying to bring it up here to keep it out of the way. But that's what a no solution case looks like here. Number 11. Number 11. Oh, number 11 might not be a special case. Okay. Okay. On number 11, we have 6x plus 2y equals 16 and 2x minus y equals 2. Now, given that they're in standard form, elimination method comes to mind, and I'm probably going to use it. However, as much as everyone wants to multiply this by 2 to eliminate y's, and you totally can, I'd let you. I'm actually going to take the top equation. Now I'm going to divide by 2. I can divide these by 2 without getting fractions. Making smaller numbers generally helps me. 3x plus 1y equals 8. Okay. So, kind of ignore that now. Y's do eliminate. You get 5x equals 10. You get x equals 2 when you divide by 5. That means this has a solution. So these weren't all special cases. I fully expected them to have, and no, they're not. So I choose a method for myself. I chose elimination. I showed you division. All good. Still got to solve for y. Excuse me. Let's use this equation that I made right here, the smaller one. 3 times 2 plus y is 8. That's 6 plus y equals 8, or y also equals 2. Didn't we have a 2-2 solution on a previous problem? I think we did. These are getting repetitive. How dare they come up with same solutions for things? Come up with something more unique. Number 12, I assume we're going to get back into the special case thing. And if all goes well, I actually hope for an infinitely many solutions case. Believe it or not, I want a special case here. I just didn't want them to forewarn us that they would show up. Negative 6x plus 6y equals 4. Pretty much the same vein as before, guys. If I can do division, I'm going to go ahead and do it. By dividing these by 2, that'll get the x's to be additive inverses. But it just so happens that the y's also become additive inverses right here. Negative 3y plus 3y. Just so happens that the constants become additive inverses, which lends us to say that the left side gets us 0. The right side gets us 0. We get 0 equals 0, which is a classic case of saying no matter what x and y are, as long as it's a solution to one, it's a solution to the other. And the lines themselves represent infinitely many solutions. So this system has infinitely many solutions. Now, I didn't appear to ever use substitution on either of these. Graphing, I never really used either. It looks like elimination did the job because they gave us standard form. It really does lend to itself for us to do that. So, hey, I'm going to use what I use. Now, maybe some of these word problems, the last 3 problems that we have, maybe we get to use substitution again here. Who knows? Let's take a look. But I'm going to use the one that's most beneficial to what we have, okay? Number 13. You plant a spruce tree that grows 4 inches per year and a hemlock tree that grows 6 inches per year. The initial heights are shown. The initial height of the spruce tree is shown to be 14 inches, if you can see that. The hemlock tree, 8 inches. Write a linear system of equations that represents this situation. So spruce tree, I'm going to let y represent the height of the tree in inches, x represent the number of years. This will be slope-intercept form. This is where maybe substitution can be used if we solve. Y equals, your mx plus b is like your rate and your starting value. 4 inches per year, 4 inches times the number of years, plus the initial 14 inches that it was. Your hemlock tree, your height for this one, it grows 6 inches per year, but it has an initial height of 8 inches. So here's our system that we can use. This would be part A. Part B, solve the system by graphing. Okay, interpret your solution. So we will graph. So I'm going to attach graph paper for you guys. Let me copy and paste graph axes here. I thought we were going to solve using substitution. You know what? I will use substitution. They say they said interpret your solution. I will solve by substitution as well. It's going to be very quick to do. All right, graphing. You know, the one issue with graphing here is my scale. Because the 14 is there, we might have to change the scale of our y's here. I hope you don't mind. So let's change both y and x scale. Let's go 10. Let's double these, 10 and 20. Ooh, I might need more. It's just too bad they're asking us to solve by graphing here because, this might throw us in a little rut. Let's go 20 and 40. Oh man, I'm not a fan that they're having us do this, which means I'm also going to go 20 and 40 here. And the only reason is so that way we can work slopes the same way we'd want to on both of these. So here's what's going on. Sorry, I'm getting a lot of texts. I don't know if you hear my phone vibrate, but I also see notifications on the corner. I coach softball, and the coaches are conversing with each other. I feel bad that I don't just close that out. But I need to know if something important comes up. Anyway, 14, listen, these are going by 4s now. 4, 8, 12, 16, 20. So 14, 4, 8, 12. It's halfway between 4 and 16. Like that. 14 and 16. 12 and 16. It's halfway between 12 and 16 is 14. Now, I can still use my slope before by going up 4 over 1 like that. Because what I technically just did was I went up 16 over 4. And 16 over 4 is still 4. As long as the scales are the same, I can still do that. I can go up 4 over 1 again. I do still run out of room doing that. So this is going to be a little tricky. I don't know. This is why I want to solve using substitution. So it's interesting that this is solved by graphing, although I don't have quite the scale for it. Now, I only care about the positive realm. Negative realm doesn't matter for us because this is asking when it says solve the system, it says interpret your solution. The question is, by what year do these trees have the same height? That's really what they're asking. It's only going to be positive years later. The hemlock tree grows faster than the spruce tree. This has, let me draw a line still for this. This has a y-intercept, hold on. This one goes positive here. Next one is a y-intercept of 8. But we rise 6. We rise 6 as we run 1. 1, 2, 3, 4, 5, 6 over 1. So the other interesting part about this, though, that I need to figure out is what I need to figure out is where these would intersect with this in mind. Don't want a 4 over 1, don't of 1, 2, 3, 4, 5, 6 over 1. Did these already cross at this point? So this is going to be really hard for me to figure out where these intersect, right? Even though I made the graph, I'm not really solving by graphing here because they intersect somewhere in between. This is not a good thing to solve by graphing with, given my scale. I feel bad if I wasted your time with this. I'm going to try and do something else with this instead. I can change scale. I don't need to start at 0. Let's try something else. Of course, I could edit out this part of the video, but this is the conversation that we have on this stuff. Let's start with this as 8 right here. It's a little weird. Start with this as 8, and let's go by 2s. Would we reach that top that we're trying to reach? I hope so. If that's 8, these go by 2s. 10, 12, 14. This is 14 right here. Let's do the same thing. These will go by 2s right here, but it starts at 0, so 10 and 20. So this will look kind of weird, right? We have 14 here. I should make these black. I guess I could have started way down there as well. But 14 here. We'll still go the up 4 over 1 like that. Kind of iffy like that. And then for the other one, like I said, I'm still going to solve using substitution. For the other one, we'll go up 6 over 1. It still didn't intersect right there. And here it passes it. It passes it at some point in between. Now, the parts in between, it still intersects somewhere in between that I can't really tell. Maybe I could have made the x's go by one thing. But here's the thing. I think it intersects halfway in between. So it intersects, I believe, at this point right here. Because that makes sense, right? This blue is 2 away from purple. Blue is 2 away from purple. Green is 3 away. Green is 3 away. So it intersects at this point. Remember, these go by 2s. So this is 14, 16, 18, 20, 22, 24, 26. The y value is 26. The x value is between 2 and 4, which is 3. So that's my solution. I'm going to double check that by solving this by substitution, which is substitute 6x plus 8 for y over here. I wish they just asked us to solve. They said solve by graphing, so it is what it is. Subtract 4x from both sides, subtract 8 from both sides, divide both sides by 2, you do get x equals 3. To solve for y, you can plug in 3 to either equation. I really don't care which one, I guess the bottom one. So y equals 6 times 3 plus 8, or 18 plus 8, which is 26. So we still do get 3 and 26, but they did say interpret, it's a word problem, interpret the solution. So in terms of interpreting the solution, we're asking ourselves, what does this mean? It means 3 years later, hemlock tree and spruce tree will be the same height. After 3 years, the spruce tree and hemlock tree will each be a height of 26 inches. That's what it means. That's the interpretation. So, as you can tell, guys, obviously substitution was significantly faster than graphing. Graphing would have been fine, but it's outside the window range. There are some old videos that I have on pros and cons of graphing. This is one of them. Graphing outside the window range is no good, really, for this kind of thing. You could have a different window range than I do. This is a solution guide video where I'm limited in my own tools, and I apologize if that was kind of a lot. And I redid the graph, so if that was a lot just to figure out that one bit. But they did force graphing on us, and those are the tools I have. All right, number 14. It takes you 3 hours to drive to a concert 135 miles away. You drive 55 miles per hour on highways and 40 miles per hour on the rest of the roads. This combines sections 5.1, 5.2, and 5.3. It says, how much time do you spend driving at each speed? So it takes you 3 hours to drive a concert 135 miles away. So distance equals rate times time. I have to process the problem. 135 miles, rate times time, 3 hours times, 3 hours times our rate. Divide by 3, you get a rate of 45 miles per hour on average. Average. It says you drive 55 miles per hour on highways, 40 miles per hour on the rest of the roads. How much time do you spend driving at each speed? Do they have to even it out exactly? Like, do they have to be integers? I guess that's the question here. So if x is the number of hours on highway and y is number of hours on rest of roads, what I have here is 55 miles per hour times the number of hours on highway plus 40 miles per hour times the number of hours on roads equals, well, that equals the 135. I don't know what I was going to do with the 45 mile per hour average here now. Suddenly, I'm sitting here wondering what my system of equations is here. If I'm averaging 45 miles per hour, okay, clearly that's being used somewhere. I need to think about that. Would I do one that... I'm thinking about this one. The average thing is bugging me. It's not 55 plus 40 over 2. Let me... Oh, it's just 3 hours. 3 hours. So the amount of hours, x plus y equals 3. I don't know why that took me so long to come up with. So I don't know if this average part mattered for me. I don't think it did. I think it's just these different totals that are occurring here. So I don't think I needed the 45 per mile average. I mean, this is the awesome part about this being genuine is I got to think about the problems as they are. I was writing down information, wasn't really relevant. This is relevant to what we need here. So time added together, distance added together, okay? Okay, from here we can solve using any method. Elimination is waiting in the wings here for sure, but if I divide everything here by 5, that just makes the number smaller, probably in a better way for me. It didn't eliminate anything yet, but I'll now have 11x plus 8y equals 27. 27. Now, with this equation, I can now figure out what to do through elimination method. Like I can multiply these, say, by -8. That would eliminate y. So negative 8x minus 8y equals negative 24. So going about it that way. So now I have 3x equals 3, and therefore x equals 1. I travel on the highway for 1 hour, is what that says. As far as y goes, x plus y equals 3, 1 plus y equals 3, so y equals 2. I travel on roads, rest of roads, for 2 hours. So I travel 1 hour on the highway. Okay. Sorry about that, but figured it out. How many miles do you drive on highways and the rest of the roads? That's where the 55x and the 40y come from. So 55 times, so that was part A, really. Part B, 55 times 1 is 55 miles on highway. And 45, how much was it? 40. 40 times 2 is 80. 80 miles on roads, rest of roads. Okay, so those are the two answers there. Okay, last one, number 15. In a football game, all of the home team's points are from 7-point touchdowns and 3-point field goals. The team scores 6 times. Write and solve a system of linear equations to find the numbers of touchdowns and field goals that the home team scores. So the home team, if you can see that little scoreboard, the home team has scored 26 points in total. So what we can look at here is, let's let touchdowns and field goals. Let's let T equal number of touchdowns. Let's put touchdowns. Let's let F equal number of field goals that they scored, right? Not the points, but the number of. Now, we do have an equation that could say the total number of scores, touchdowns, and field goals together equals 6. Scored 6 times. And 7 points per touchdown times the number of, plus 3 points per field goal times the number of, is a total of 26 points for the home team. So these two together create a system. Now, I've done a lot of elimination so far. Should I do substitution? No, I'm going to use elimination if I prefer it, and I do prefer it here. So I'm going to multiply by -3 and eliminate the f's. So -3t minus 3f equals -18. Just kind of ignore that one for now. And here we will get 4t equals 8, therefore t equals 2. 2 touchdowns were scored. How many field goals? T plus f is 6, 2 plus f is 6, f is 4. Seems like an old 49ers game. The home team scored 2 touchdowns and 4 field goals. And that's it. All right, guys. So despite my hiccups on numbers 13 and 14, getting some things done in a timely manner like I should have, my processing, I think, is legitimately important when it comes to you thinking about how problems are done. It took me a second as well, and I got to it. But we are there. And y'all, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Hopefully that you learned things as you went. Maybe you beat me to times on graphing and setting up equations to solve and things like that. But we're there. Thank you for watching for sections 5.1 to 5.4. We still have a few more sections to go in this chapter involving inequalities at some point. I think by 5.6 we're going to hit inequalities again. Thank you so much. Take care. I'm going to see you in the next one.